So, welcome to Boston Python's presentation night. Tonight we have a presentation by Scott Gustafson introducing CircuitPython on hardware. CircuitPython, if you're not familiar, is for running Python on microcontrollers, so very small embedded computers. And Scott is going to walk us through the basics, everything from blinking an LED to building a web server. As a little bit of an intro, Scott is the owner and principal developer of Garlic Software. He's got a very long career. His love affair with Apple spans 20 plus years, he's put in his bio. And I'm really excited to hear what he has to show when he has to tell us about CircuitPython. I've seen a little bit of a preview of some of the hands-on demonstrations here, or maybe not hands-on, but virtual. And so without further ado, Scott, take it away.
All right. You should all see some slides. So, about me. A bachelor's in computer science, and I'm going to go through this really quick. Master's in software engineering. I've been writing software for a very long time. I've worked at lots of big companies and lots of little tiny ones, done all kinds of stuff from firmware and device drivers, embedded systems. And I've taken some fun classes in electronics. I am not an EE, so don't quote me on everything here. I know some things. You will blow up CPUs and things, but that is also fun. It's part of the learning. All right. Why are we here? I like to paint miniatures. I was going to a gaming conference, which I go to a lot, and I take classes on how to paint. And I was at Las Vegas, and I saw some people playing this game called Marvel Crisis Protocol, and it looked a lot of fun. It was based on superheroes, so all the X-Men, all of the, Superman, well, not Superman, that's DC, sorry. But all of the Marvel characters, so the Avengers, and it was so fun to watch. And part of the game is you have to have terrain. So the Hulk basically can throw things, and he can throw buildings and trash cans and small things up to a certain size. And so they have these different size limits. Traffic light turns out to be a size 1. And Hulk can throw that all over the place. So can Magneto. Magneto can move it around. All right, so why is this interesting? Because I like painting miniatures. So here's a couple of garbage cans, for example, that I've painted. And you can see the rust. And there's a quarter there for just size references. And this is a clear character of mine for a different game. But when I saw this sprue, this is a plastic sprue out of the game for traffic light. And I just see this and I think LEDs. I have to light this up. I have to make it blink. I have to make it look realistic. I want to set it down on the table and have people just go, oh, that's so cool. Well, that's my goal. So we're going to work towards that goal. So what do we need to know? We need to know how to use a diode. A diode is basically a component that conducts electricity or conducts current, I should say, in one direction. The symbol here for the electrical symbol has an anode and a cathode. That's basically your positive and your negative. And there's a little black band on the diode. You can see it in the picture here. That just tells you where the cathode is, so you know. LEDs are diodes. It's a light emitting diode. When the current flows through it, light comes out of it. So this is why we care about what diodes are, because we use them all over the place. You may not know all of that. You may just call them LEDs, but they're actually diodes under the hood. Lots of different shapes. So this is basically what's inside the diode. There's a technical diagram here, but again, anode, cathode, positive or minus. The symbol next to it on the right is basically our symbol for a diode with little lines coming out of it. It's just showing the light coming out of it. That's all we really care about. Most people understand what a diode or what a LED is. Resistors reduce the current that flow through them. So diodes, that's current flow through. Resistor reduces that current, so we don't send all of the current through. Again, some common resistors are pictured here, along with the electrical symbol for a resistor, which is a little jagged line. If you're interested in playing along at home, you can pick up some of these little, this is an example from Make company. They make this little survival pack, and it just has a bunch of little components in it. Call these passives. So there's a bunch of, resistors, a few LEDs, a little breadboard, a little thing to plug in some power, some other capacitors, other things. These are like $20. You can pick them up. Lots of different varieties. Make is just one. SparkFun, I have a link that I've posted to the Slack channel that had all of the things that you can buy to follow along in the course, or to play it along later. And that is one of the ones I have, I think, a SparkFun one in there. They're the same thing, $20, comes with a bunch of little things. So what do we get? So we get here to this LED circuit. I have a battery, which is the V. I have current, which is the I. It goes through the LED, and it goes through the resistor. And that's how we get light to come out of our LED. The reason we have a resistor is if we send all of the current through the LED, it'll just blow up. And not necessarily blow up as an explosion, it'll just make a bright flash and fry itself. So if you're playing with LEDs, make sure you're using a resistor to limit the current. So what are we gonna do? I'm just gonna show you how to do it. I'm gonna show you a Raspberry Pi, which is a $4 device you can pick up at many places. These ones I get at Adafruit, they're $4. And this is for the non-Wi-Fi version. All right, so you should be able to see the camera and the, let me make this just a tiny bit smaller. Oops. All right, so we got a camera, we have a Raspberry Pi Pico, we have an LED, we have a resistor, and it's basically just blinking. This is the code that is running. So I have a very simple example, which is import board, digital I/O, and time. I assign a pin, which is my digital I/O, digital in and out board A0, which is this pin right here. And I'll show you in a little while the schematic for that, or basically the diagram so you can see where the pins are. And then while this is true, I have a pin that I'm just flipping the value of. So if it's 1, I change it to 0. If it's 0, I change it to 1, and then I sleep for a second. And just for an example, we can comment out this line, uncomment this line, save the code, and watch our thing blink even faster. So we can live edit right on the device. It is mounted as a USB mass storage device. I have access to all the code that's on it. And as I change it in Visual Studio Code, I can actually see the results of my program right now. And again, we can easily change it back, save it, and we go back to our slow 1 second display. All right. So again, that is a Raspberry Pi Pico for $4. Those LEDs and a resistor, those are a couple pennies. So for less than $5, basically, you can put this together and try it out and have some fun. So that was the example we saw. This is the demo code, just to show you what it was doing very simply. It just imported a few things that it needed. Again, made it our pin, which is on port A0. And then we turn that to an output pin, and then we do flipping the value over and over and waiting a second. So this brings us to, why do we have analog and digital pins? And so digital is either 0 or 1 from our output standpoint. So I was using this as a digital pin because LEDs need a solid constant current to light. There's a threshold where they won't light. So if I had to say 1 volt, it probably wouldn't light up. It would just be off. But this is 3 volts or 3.3 volts, so it lights. Our digital pins, we generally call them GPIOs because they're just general purpose inputs and outputs. Analog pins, on the other hand, allow you to have that variable voltage. And so since I'm using 3.3 volt things today, for examples, I can vary the voltage output from 0 to 3.3. Now, I know I'll get into this in a little bit, but you can't dim an LED. And some of you might have gotten like LED light bulbs for your houses when it was all the rage. And then you put it on one of those old-fashioned dimmer switches because that was in your house. And the old-fashioned dimmer switch like worked perfect to dim your incandescent light bulbs. But as soon as you put in the LED one, it just was either on, or as you turn the dial or move the value down on your switch, it just turned off. So I'm going to show you how to actually deal with that. But not all of the analog pins that we have on these microcontrollers are both input and output. So this is there was actually an interesting talk about from the Eben Upton, the guy who does Raspberry Pi, who founder of that. And one of the big differences of why they don't include the inputs for the ADCs, or no, for DACs, for the digital out in this case, is it's like 20 cents, but only like 5% of the people use them. So they don't include those. So if you're actually looking for those kind of things, it's important to look at the specs and see if the particular board or the microcontroller you want to use actually has it. But if I'm doing input and I'm doing analog voltage, I need an ADC, an analog to digital converter. That takes my analog voltage from say 0 to 3.3 voltage, somewhere in there, and that converts it to a digital value I can read. So I get back basically a percentage. So if I'm at 1.6 volts or so, I'm going to get my 50% approximately back. Same thing with output. You need a digital audio or digital to analog converter, which is how we go from, say, I'm going to set this pin to 50% and I get back the right value, or I put it to like 66% and I get 2.2 volts. So you just have to watch out for your particular kind of microcontroller, and I'm going to cover several examples here. So you'll see which ones have DACs and ADCs. So for this Raspberry Pi in particular, this example, I was blinking pin A0, which is the ADC0, which is pin 31 in this diagram. And these diagrams are on the product web pages, basically for every vendor who makes these things. And they're really easy to generate for folks who need them, but generally all the vendors provide them because they're super helpful. And I'll show several examples as we go. So it's important to remember that microcontrollers are not full-blown computers. They have very limited RAM and flash, the drive space where you can actually store your app, and then how much memory your app can actually consume while running. So say, for example, you wanted to show a large JPEG image that you had downloaded off the web and you wanted to display it onto your display. Well, your microcontroller may not have enough RAM even to decompress the JPEG image to convert it into the RGB values to display. So you have to be very conscious of the size of things. And they're also much, much slower than normal CPUs. So keep that in mind. These are not running blinding fast gigahertz speeds. These are running at megahertz speeds. A few examples are from right to left here. There's an ATtiny4 along with some grains of rice for size reference. There's the ATtiny85 on a quarter, and the Raspberry Pi 2040 microcontroller that I was just showing on the Pico. So these are just some examples in sizes. But what we have is there's different capabilities of each one. So the ATtiny, even though it's an 8-bit computer, it runs at 12 MIPS at 12 megahertz. So it's running 1 million instructions per second. So 1 instruction per hertz, which is pretty good speed. But again, you're limited to 8 bits and your program space is 512 bytes. That is super tiny. And you have 32 bytes of RAM, which is also very tiny. And I did a project with that, and I'm going to show a picture of it in a second. And there's a write-up there on my blog if you're interested in reading about how the firmware was written. Then there's the AT85, which is also running at, it's an 8-bit, and it runs at 20 MIPS. But now if you look at the Raspberry Pi 2040, it's a 32-bit, which is awesome, not quite 64, where our CPUs would be. But it's a dual Cortex ARM M0 Plus, and it runs at 133 megahertz. But the important part is it's only 3.3 MIPS. So it's not quite as fast as the 8-bit computer. But the reason why is because it's actually reading all of its program from a separate RAM chip. And so when it's an uncached chip or uncached instruction, it actually has to load all of that from memory. And so that takes time. So once it's loaded, it actually runs really fast. So you actually want to make sure you're keeping your blocks of things underneath your RAM limit, and you can actually run quite fast. So an example of the AT94 was this product from Adafruit, was the iNecklace. It has firmware, then the LED and AT94 are underneath it, and the LED pulses and the pulsing effect through the CNC cutout there. It was a fun little project. It's written in assembly. All right, so we're gonna get CircuitPython. So CircuitPython is a beginner-friendly version of Python for microcontrollers. It's a fork of MicroPython, and there's the two URLs for the two repos. You can go look at the CircuitPython repo, and you can see that it's clearly a fork of MicroPython. They make no mistake about that. CircuitPython.org, they have the all the downloads for all your specific boards. So I'm going to show an example of that real quick. And that's where you can actually download all the libraries and community bundles, which is super helpful. So if we go to the website here. So this is the circuitpython.org website. This is the landing page you get to. Up here at the top is the downloads link. You want to go into here and you will see all the different kinds of boards that are available. There's 410 boards right now, so plenty. This is, for example, the Pico, and I'll bring up the Pico here, and you can actually see the 8.05 is the latest version, 8.1 is the current release candidate that's coming out. But the important part that we care about is this built-in modules. So this comes with a whole bunch of things already set up for the beginner. So you don't have to go and say, oh, I'm going to include all this code and go import of all of these things and compile in all of this firmware. You can actually just go right out of the gate. Some of the best stuff is the display IO, which I love. It just makes making simple displays very easy for you. And you'll notice that one of the ones that's missing here is the Wi-Fi. And if we go look at the Pico W, you'll see that Pico W has the Wi-Fi built in. So they've done a lot of the work for you by defining all of these different boards and defining all of the different things that you are going to use on a regular basis. Let's see. All right, so the important part also is the download U2F. So this is how you get this particular binary. And so you just download the UF2 file. That is basically the disk image that's compiled that you're going to copy over. And I'll show an example of that in a minute. The other thing we care about is this libraries tab at the top. And so if you go in here, and there's basically two versions of these libraries. There's the MPY compiled versions and the PY full source. So for most people, you're going to just want the MPYs. Pre-compiled, smaller space, you can use them, they'll go faster, good for you. If you're like me and are learning Python, it's really, really nice to have just the plain old source code. So I actually use all of the Py bundle to give me all of the source code. So I can actually go inside of it and look at everything because I want to know how it all works. And this is not, again, we're not running blinding speeds here. I don't really care if it takes an extra, few milliseconds for it to, compile at runtime. Don't care. It's important to note that the examples are included in the full bundle, so you don't have to download the examples too. There's a lot of great examples of how to use all the different kinds of features. So those are really helpful. Community bundle is the last part that you want to grab a copy of. Again, there's the source itself and then the MPYs. This has a lot of other drivers that people in the community have provided that, for example, Adafruit doesn't provide because it's not one of their chips that they sell. So a few folks have written some for WaveShare, for example, which is a vendor from China. All right, so that's that one. Go back here. All right. So I showed you the website, how to download the library's community bundle. And the built-in modules are the important part, which is just seeing what's built in there. Board is going to be one you're going to use quite a bit, which is to get the board pins and the board specific data. I'm going to show some cheat sheets on what some of those things are. And microcontroller, if you want to actually get into some of the more details in the microcontroller, there's a package for that, so you can actually get to the pins through that as well. So some pins won't be defined through board, but they'll be defined in microcontroller. Let's see. So I'm going to do a demo of how do we install CircuitPython on a CutePy 2040. And so this is if you see my people face, this is a Adafruit Raspberry Pi 2040 sealed in the bag here. And we're going to take it from cutting it open to installing it and get on the way here. So let me just reposition this little camera here. So we take our CutePy, and so there's a tiny boot button. If I hold it really still, you have to hold in the boot button when you're going to install a new OS. So I'm going to hold down the boot button and I'm going to get the Raspberry Pi bootloader to mount. All right. So here I have the Raspberry Pi, so RPI RP2 bootloader disk image that is mounted. And I have a Adafruit CircuitPython for the CutePy RP 2040 English 804 version. This is how hard it is. You drag and you drop. It's going to copy, it's going to reboot, and it's going to mount the CircuitPython disk image. So copied, it is in the process of rebooting. And just move this one out of the way. And there's our CircuitPython. There's our code that's running and empty library. And if we look, there's the code that's in it. Hello world. All right. All right, so we took a these ones are $10. These CutePy 2040s. I really like them because they're super tiny. And again, going from the standpoint of I want to put this into a little tiny street light that's gonna or little tiny traffic light for a game. I want it as tiny as possible. All right, so it shows up on your computer as a USB mass storage device. CircuitPy is the name, and it has a lib folder. The boot.out just tells you what the boot state was and tells you like what version was in the was loaded. And settings, we'll get to that in a little bit, but that's where you can put basically global variables that you want to access. All right, so Raspberry Pi 2040. These are dual core ARM Cortex M0 Plus processors. They are really nice little things. They're super inexpensive. Again, $4 for the one official Raspberry Pi version. If you just want to start playing with it, you can buy just the chips if you're really ambitious, and I'll show you some examples where people have done that. There's some really nice features of it, and low power sleep actually caught my attention because, again, I'm going to be running this, a traffic light. It's not doing a whole lot. It's flat. It's basically showing a light, and I want it to sleep all the rest of the time to make my battery last longer. I'm going to show you why I care about that and how I was able to change some of those features. Anyway, it's got lots and lots of ports and buses, and it has lots of lines for doing all kinds of stuff. So, for most people, this is going to be plenty of power for doing all kinds of little things around the house. The Mu editor. So I don't use the Mu editor. I know it's the official editor they recommend you use. You can go to this codewith.mu and download it if you feel like it. Hey, knock yourself out. I like Visual Studio Code. I like all the nice highlights. I like the way Python works in there. The benefit of this is it does give you the REPL output, so you can actually see the straight into the serial port of the microcontroller. I just use terminal. I don't mind. So that's just for reference. So if you want to use Mu, go right ahead. Now, I'm going to show how to use multiple LEDs on another device, which is, again, another Adafruit version. This is a KB2040. It's only $9, and it is a little bit bigger than the Cutie Pie, and it's a little bit smaller than the Raspberry Pi. So, So again, we're just trying to get to the point where I can have wrong demo. But the beauty of all of this, one second. I just replaced the demo live. There we go. So now if I just click over here, so this is the code that's running. This is 3 LEDs. So now this is the same thing as basically having the one LED. I got 3 pins, red, yellow, green. I have 3 basically 3 pins set up, and then I switch them all to output, and then I just go through and say, hey, set the red, set the green, set the yellow. It's either 1 or 0, and sleep 1 second between each one. Very easy to get your LEDs to blink like this. I'm like so close to having a traffic light set up. I think this is almost there. And I'll show you some examples of why I don't think I'm quite there yet, but I think it's really close. All right, let me see what else. Okay, that was it. All right. So it was just a simple board. It's a KB2040, 3 LEDs on 3 different pins with 1 resistor, and I was only lighting up one thing at a time, so I didn't really care that I had only 1 resistor. So pulse width modulation, PWM. This is how we dim LEDs, because incandescents dim by voltage. So if you have one of those dimmer switches in your house and it has 110 volts in your house and it's got an incandescent light bulb and you're turning that down, it's going from 110 volts all the way down to 0 volts to off, and it's variable in between. Well, if you try that on an LED, it doesn't work. So once you get past the threshold voltage, the LED just shuts off. And once you go above the threshold voltage, LED goes right back on. So PWM sends out pulses of power and then turns off. And so it's quickly turning it on and off to trick you into thinking that it's lit, but it's actually not. It's actually going on a duty cycle, we call it, to change the brightness. So an example duty cycle would look like this, which is like a 50% duty cycle. Would have 50% of the time it's on, 50% of the time it's off. So that'll give you about a half brightness for an LED. And the higher your duty cycle, the brighter it's going to be. The lower your duty cycle, the dimmer it's going to be. So I can show this. So on this particular board, we'll switch to a PWM. And again, I'll just replace the code live. And so now what you're seeing is basically I've taken this to a PWM out. So I'm not doing a digital out anymore on this pin. And I'm saying, okay, the duty cycle is basically 100%. Wait a minute, or a second. Go to 50%. Wait a second. Go to 10%. Wait a minute, a second. And then just keep going over. So you can see that the LED is going from bright to a medium to a low, and then bright, medium, low. So that's how you can trick the eye into thinking that the LED is actually dimmer, but it's actually not. It's actually just flickering really, really fast. In this case, at 5 kilohertz or 5,000 hertz, which is there. All right. So another example, and I'll drop the last one here, PWMs. I'm just replacing the code again. So now I have red, yellow, and green, 3 different PWM outs. And I'm using 3 different PWM channels basically in this microcontroller. They're all independent of one another. And I'm just setting the duty cycles to different things so that they all 3 can run at different scales and different speeds. So you can see that there are 3 full PWMs going out. And that's important because not every chip's going to have multiple PWM outs. And some pins are going to be tied to other pins. So if you do a PWM on, pin 1, pin 2 might be the exact same PWM. So if you want a second PWM channel, you have to go to, like, say, pin 3 or 4. And then the next one might be 4, 5, or 5 and 6. All right, so that's just an example of blinky and dimming lights. All right. So one of the nice things about these is we have these other LEDs called neopixels. And that's, I believe that's an Adafruit licensed name that they have invented, but basically it's an RGB LED. And this is just showing where it is on this particular board. It's that little lighter area, or the area that's not kind of alphaed out. And I'll show an example of what that actually looks like. So this CircuitPy 2040 has one. It's labeled Neo here on the screen on the front side. And if you see it there, oops, go back. You see it there on the screen, the Neo that's silk screened. And again, this is showing the pinouts for this particular board. It has a neopixel and a neopixel power defined at the board level. So in the board package, you can say, oh, well, just give me the neopixel, and it knows what pin that's associated with. And that's actually GPIO 12 in this case, or as you see, PWM6A, but you're actually not sending PWM to the neopixel, you're actually just sending some data bytes through that. So this is what an RGB surface mount LED looks like. This is really high magnification. There are 3 different colors in here, RGB. You can have a 4th color sometimes, which is white, to give you a little more pure white. This is what a neopixel looks like on the inside. So it has the same RGB, but it actually has a chip in it that's taking care of all the PWM for you. So you can actually vary all the values of your RGB from 0 to 255 to go from off to fully on. But the chip takes care of all the PWM, so you don't have to manage any of that. You just set it and forget it. And I will show an example of that. Here's another vendor, Seed, who makes these XIAO compatible size. That's basically the same size as the Cutie Pie from Adafruit. Again, you can buy these at Amazon for $26 for a package of 3. So they're comparable prices. So I'm going to show you a demo of NeoPixel. And so take one of these guys. So this is a Seed Studio version. Let me get this to sit super flat here. All right, and there's a little piece of film that's dampening the output of that LED so it doesn't blind the camera, but you can see the individual pixel, or the individual color LEDs inside of that one pixel that's in there. And again, this is just this code, which is basically NeoPixel, and you do board NeoPixel. That's how easy it is. And then in this case, I'm just going for red, green, and blue, which is RGB, in the range of 255, and just cycling through all the colors, and then sleeping while we wait for the actual pixel to update and show the colors. So it's just going to cycle through the RGB values. So that's how easy it is to work with random colors in your design. All right, so the other thing you can do, sorry, I forgot to set this one up. Let me, all right, hopefully y'all can read that. So I'm connecting to the serial port. So every time you plug one of these in, it creates a serial port on your computer. And I'm just going to break into the REPL here, and you can actually do stuff like import board, enter board, and see all of the different things that you can actually access straight from the device. So in this case, the NeoPixel is what we cared about. You can import the microcontroller, and then also look at that. And see that, you know, we have a slightly different set of things, but if you want access to any one of the particular pins that, like, it doesn't have a pretty name to it, or you just say, hey, I want to attach to pin 5, and you can go to that instead of actually knowing what pin 5 really is. So that's one way to get into these, and if you just Control D from here, the code starts running again, and we're just connected like normal. All right, let me get out of that. All right, so we're close. We got LEDs. I have one LED to make all kinds of colors. I want to make my stoplight. Pretty close. So we have this thing. I come from a computer science background. Back in the 90s, this book came out, Design Patterns. It was super popular. Since then, there's been a whole bunch of books about anti-patterns, and some of these design patterns were like, hey, you should not use these things. But one of these I actually liked. One of them is called a state machine. Because when I think of a stoplight, I think of a state machine. Because I can't have both the red and the green on, for example. So those are two independent states. And I need to be able to say, hey, you're either in the red state or you're in the green state, or say you're in the yellow state, or hey, you're the walk sign is on, or the don't walk sign is on, or some other thing. So a way to explain some of the state machines, a light switch. It's on or it's off. It's got two states, on, off. I have my traffic light, 3 states, green, yellow, red. And there could be fancy ones based on time of day. Maybe I have a flashing yellow at certain times of the day or night, or flashing red at certain times of the day or night. Anyway, simple example, 3 states. Walk, don't walk. Again, 3 states. You generally have a walk, then you have some flashing don't walk saying, hey, stop, it's about to be done, and then the solid don't walk. And then when we combine them all, now we have how many states? Well, there's actually only 4 states in this particular case, because the green light is the only time that the walk and the don't walk are changing, is when the green is on. So when the green is when the green is on initially, the walk comes on. When the green light changes to don't walk flashing is before the yellow light comes on. When the yellow light comes on, the don't walk is solid, and then our red light and don't walk are solid. Anyway, so 4. So I'm really, really close now to making my traffic light. And I'm going to show you an example using this pixel array, which is a whole bunch of those NeoPixels, 25 of them, and a state machine. So let's pop this guy out. And I need to see which way this one is. Okay. So I'm going to have to hold this one a little bit. All right. So in this case, I have 5 pixels that I'm actually using out of this entire array of 25. So I'm using pixels basically 1, 2, 3, 12, and 17 as shown here on the screen. And I've just defined some colors. So I have red, yellow, green, white, and off. And so as I have my green light, I have my my walk stage, and then we go to the flashing don't walk, then we go to the yellow with the solid don't walk, and then we have a red with solid don't walk, and then we just keep cycling through that. And I want to show you the state machine code, which is the important part. This is why I use a state machine, because this is the important parts. So I have a machine that I can make a state machine. I add a state, the green light, the don't walk blink state, the yellow light state, the red light state. I have machine start, and then in my loop, I do machine update. That's basically what a machine state machine does. Now, there's a lot of interesting things in this code, which we're not probably going to go over all of it, but I just want to give an example of what this state object is. I'm going to let go of this thing. So a state object basically has some time and an enter, exit, and an update. And by default, they don't do anything. Individual ones are going to override each of those. And our state machine basically has an add state. We have a start, and this is a linear state machine. We're just going from state 0 to state 1 to state 2 to state 3, and then back to 0 to 1 to 2 to 3. I needed a very linear one for this. There was no fancy states. You can have all kinds of fancy states. And so in this case, we just go, when we go to next state, we're just going to +1, and then we're looping over the array of states that exist. And the updates just basically call each state's update and then does some kind of sleep. So for example, a red light state can be defined here as I have a red light sleep time, in this case 5 seconds. I have an enter condition, which is when I enter this, I set the red light pixel to red, And when I get out of the red light state, I turn the red light off. So that's how simple this kind of state pattern is. The yellow light is the exact same thing as the red thing, just with yellows. And the green is a little bit more complex, and I'm not going to go over all of this. But basically, the green has a blink state, and the blink state actually does an update. That's why we have an update which calls the blink for a number of times based on your settings. Anyway, so that is pretty much all of the way to getting to my traffic light example. So I'm going to basically implement my traffic light with the walk, don't walk, and a few of these neopixels and this state machine code. Now, one of the important parts I was talking about and alluded to earlier was the sleep. So if I want this to last forever, I need to do something in sleeping. So when I ran this in sleeping with this time sleep, with this for all lengths, when I just had plain time sleep, I was getting 5 hours of battery life for my tiny little battery. And I have this example here on the board. This tiny little I have this tiny little 150 milliamp hour LiPo battery, and I can get 5 hours of that just using regular sleep. Well, one of the nice features, there's two features in this microcontroller land generally, is there's a sleep until I alarm. So there's kind of like this, hey, just basically pause everything, and then when the alarm goes off, wake back up. That's called a light sleep until alarm. And then there's also a deep sleep state, which is exit in deep sleep until alarm. And so I tried out this light sleep until alarm, and I gave it basically for any time that was over a second, we'll try to go into this other sleep state. And anything that was less than a second, just keep doing your normal sleep. Well, this went from 5 hours of battery down to, or up to 7 hours of battery. And why do I care? Well, each game of Marvel Crisis Protocol is an hour and a half. So I can now have multiple games before I have to recharge my batteries. That's important to me. All right, let me go back to slide here. So in this time sleep, I was getting 5 hours. With the light sleep, using the light sleep until alarm, I was getting the 7 hours. And then there's the exit and deep sleep. So right now, Raspberry Pi 2040 doesn't have this implemented. Some other microprocessors do have this functionality built in. Most of them actually have it. Like the Raspberry Pi has the ability to do it. It's just not implemented yet for Raspberry Pi. The important part of this is what you wanted to do is save the memory state of at least some part of your memory in a non-volatile state, so you know where you were, for example, in your state machine. So when you wake back up from sleep, you can resume exactly where you left off. And so right now that's not implemented, but I know it's being worked on because I saw some GitHub issues logged against it. Anyway, so 7 hours, plenty of time for me to get in like 3-4 games of Marvel, and we're all good. So I have all the pieces I need. My crisis is averted. All right, so we're going to blast through some fun demos now. So I2C, it's a 2-wire control bus, and basically you have a clock and a data. As the clock goes up and down, you're flipping the bits on the data line. Again, most of this is all hidden from you. You can actually bit bang it yourself if you really want to. You can control all the pins yourself. You could do all of it. But the Python code in CircuitPython is there for you, so you don't have to do any of this. It's really 4 wires, and I'll show you the connectors that we actually use here for the stemmas, because you need power and a ground, because you're sending it out to another board. But basically, it's on your microcontroller, you can have many other things on your I2C bus, and you can address them all by, they all have little addresses. So sidebar, there are many other examples of these kind of boards at Amazon and other vendors. This is just Maker Focus, which is Amazon's branded products. Of note here, and I have both these here, but I'm going to show you the top one. Notice that the OLED display here has yellow and blue. That doesn't mean it's two color everywhere on this screen. And I'll show you what I mean. That means it is two color. The top part, the first few pixels on the row are yellow, and the rest of it's blue, just as a note. So I'm going to show you that in a second. So I'm going to show you some I2C over the stemma connector, an OLED display, and showing some basic text like hello world. All right. And for this, we are going to use Minifig Spaceman. All right. Have to kind of hold this so we can keep everything in frame here. Again, I have a piece of film over the screen so the LED OLED screen doesn't blast out the camera. Again, let's see if I can get it. All right. Anyway, so hello world is displayed. This is the code. So display IO is a very simple display functionality for working with these kind of displays. It takes care of all the groundwork for you. I'm here. First thing I have to do is release the displays. If I don't, if you just run like hello world, you can actually, it'll output hello world onto your screen. You don't have to do anything. It's already set up to do that. But I want to show you the I2C bus. So again, this is just going to the board, stemma connector, I2C0 in this case. This one actually has multiple I2C buses. And it uses this tiny little cable. If I flip it over, these are the stemma connectors basically, and this tiny little 4-wire cable that's here. So just go back to the hello world. All right, so what this is basically you get I2C, you set up a display bus using the I2C display, and you give it the standard device address. Each vendor will have their own device addresses. Most of them, for these ones, are standardized at 3C. You can tell it what width, what height. And in this case, I'm using a border. So if you see there's a border of 1 pixel. And in this example, it's just creating a color bitmap of white in the background, the entire screen. It adds that to the display. It creates a black bitmap, 1 pixel less, which is the border width, to fill in the white. And then it adds that, and then it adds a text label for hello world and plops that down at 28x and whatever the dimension of hello, the height, divided by 2 minus 1. And then appends the text. So for example, if I went and said, okay, I'm just going to take out all of the inner rectangle and the label, I should just get a solid block. There's a solid white screen. Similarly, if I just say, oh, well, only do the text, don't bother even doing the background with the border. So as the simplest example, I have a display and I just say, oh, put the one label in it. Oh, what did I forget? Splash append. Oh. Commented out the important part. There. So I have just simple hello world. So it's very easy to draw on these little screens. This comes in really, really handy when you want to display something interesting. So let me show you one other example on this one. So I'm going to unplug the minifig. And this is an example of using a 2040 to drive. This is that blue and yellow screen, and here you can see the flickering of the refresh rate for the LEDs and the camera interaction. But you can see the top few pixels, the rows are yellow, and then the other ones are blue. So this is what they mean by yellow, blue, OLED. They don't mean you can use yellow and blue all over the screen. They mean only in this area it's always yellow, and only in this area it's always blue. I was disappointed when I got these. And again, that code is just simply doing the same fill in a box. All right. So the other interesting displays are on SPIs. So as you start doing a whole bunch more I2C stuff, you'll find out your I2C bus gets a little crowded, and sometimes it slows down because it's trying to display things, also trying to read sensors and other things. Well, SPI is actually much better for putting your display on, and you can actually have like full color displays. So I'm going to show a couple examples, and these are generally 4 wires as well. The important wires, right? So you have the same serial clock. You have the master out, slave in, master in, slave out, and then the slave select lines. There's also ground and power. So there's really 6 lines, but 4 is what we care about, just like I2C is too. But the nice part about these is you can get all kinds of fun examples, like this one. Let's see which direction this is. This is this direction. So, yes, in Marvel Crisis Protocol, Spider-Man and the Doctor are both in the game. But again, this is a very simple RP 2040 with a built-in LCD, so it makes your life really easy. You don't have to even do anything else because it's all built in for you. And the code is just simply, there's where all this code comes from, this particular example code, and you basically just tell it, here's the port, the pins I need for the display. You set up your bus SPI, and you set up a display bus, tell it what kind of display. In this case, it's an ST7735R. And all it's doing is opening Spider-Man, No Way Home, BMP, and putting that right on the screen. And that's it. Like, that's simple. All right, that's one. And one more. This is another wave share one. If I can get it to sit still here. Let me turn off a couple lights so get it to adjust. All right, so this is if I zoom out a little bit, you can see, it looks like a watch face, circular screen, and it has scrolling text that's going by. And again, we're blowing out the screen with the text. So I go in close here. It's a little hard to read, but it does look nice. And it's basically one of these other kinds of screens, and uses the SPI bus. This particular example from WaveShare actually has gyroscope, has temperature sensors, it has a whole bunch of other peripherals. all available over on Amazon. There's a link to it in the big link of stuff. And if we go all the way down the code, this is basically all it's doing. It's doing this demo loop, which is drawing the rectangle, drawing the title, and then while we update the time, we're just moving the title over a pixel at a time. So it's scrolling across the screen. There's a whole bunch of setup code that is specific for this kind of display because it's not supported by all of the built-in CircuitPython stuff. But it's kind of fun. All right. So all right. So next, we're going to show slightly different. For this, turn the lights back on so we can see. Wait for it to catch up. All right, so this is an example. If it'll catch up here. All right. So this is a ESP32 device. Now with ESP32s, we get Wi-Fi for this particular vendor, Expressive, who makes these. And here I'm just showing the code of, again, this is the same code you saw before, which is basically set up an I2C display using the stemma I2C, set up a simple display bus. This is a 128 by 64 screen. It does the exact same, create a white for the border that's around the edge, create a black bitmap for the inside, and then inside of that, write one text, which is the Wi-Fi radio IPv4 address. So right now, this device has that address. You see it occasionally reboots because I'm on plugged into the USB and the computer's accessing it. That causes reboots. So now I have basically the capability to do whatever I want. One of the nice things about these little guys, and this is 90.8, is one of the built-ins. So if I go to 90.8, I have a full Wi-Fi, full server in there to let me see what this device is. So it's an Adafruit QT Py ESP32S3 running 804. And I can actually go look from here at the full code. So let me put in the password. Yes. Open code.py. And there's the same code that is in my Visual Studio editor. So if I bring Visual Studio back up, there. So there's this is line 45 here is line 45 here, the same Wi-Fi IPv4 address. So I can actually get access to this from without even having a code editor. I can actually do it fully in the browser. Same thing as if I go to the serial terminal. I can actually access the serial terminal, and I can Control-C out of the code and just hit return, and I can then do things like import Wi-Fi, and then do print Wi-Fi radio IPv4 address. And you can see I can get the 192.168.90.8. So the nice things about these, you can actually put it on your wireless network, and it just works, and you don't have to do anything else. And Control D continues the code. All right. So nice little interface for folks. All right. Next, I want to show. Get rid of this one. And that was it, just in a 3D printed case that I had made because I wanted something to hold it. This is another Adafruit feather. Oh, let's. Again, on the Wi-Fi, and I'm doing the same kind of things. This is an SPI display that's built into this Adafruit feather. Do the same display bus, the same kind of display, the ST7789. And I'm doing the same thing, setting up a bitmap in blue color in this case. And see if I can let go of it so I don't have to hold it. There we go. All right. And then here, it connects to does the radio connect. And it's doing the OS get environment variables to get the CircuitPy Wi-Fi SSID. That's out of that settings file that I showed earlier. And if you look in here, there's a settings file. I'm not going to show that because it's got passwords, but that's how you get the SSID and the Wi-Fi password from the OS environment. And then you can just tell the radio, hey, give me some sockets, HTTPS, give me my default context here. This is returning back a quote from CNBC's quote service. And there's some JSON sanity checks here to get to the important part, which is the data short name and the data last. So in this case, we're looking at the S&P 500, and the last value right now is at $4,198.05, and it's just showing the display. So again, I have a tiny little device with a tiny little screen that I can set up as, querying a web service anywhere, anytime. So the next thing you can actually do, let me zoom out a little so you can see how tiny that thing is. Again, I just 3D printed a little holder for the Cutie Pie and a tiny little temperature sensor. So again, if I just look at the code, we have a Celsius Fahrenheit conversion. Again, we have simple I2C bus. We're just looking at the stem I2C, which is this one little connector, simple little cable connecting to this other sensor. And it also has a Wi-Fi radio. And if we go to, bring my browser back up here, this is what it's currently sending out. And the data endpoint has a serial number, relative humidity, temperature. I'll go back and look at the code. So you can see here's connect to the Wi-Fi just like the previous one did. Create a server. The server route is the /data. And then it has a temperature, relative humidity, and serial number. And those are the three things. It's just reading straight off the sensor. You don't have to do any special functionality to talk to the I2C. It's all being handled. It's querying the sensor every time you're going through the /data call. And so all this is doing is simple server start. And if it doesn't start, it resets. And then while it's running, this particular sensor type has a special little heater built in, and the little heater needs to be kicked in every once in a while. So every 100,000 loops, it'll kick in the heater for a second and just keep this the humidity sensor kind of working right. So basically, that's how you can basically set up a simple sensor. So if you want to have like temperature sensors all over your house, this is a really simple example of doing that. And you can query it through an API that you create. All right, last demo. This is the fun one. And I see some people are screwing around already. Some people have seen this. So this is, let's see if I can get it into focus here. So this is similar. This is a Adafruit Feather. And I'm going to zoom in a second. And it has a sensor on it. There we go. You all can see that as a temperature and humidity is constantly updating on screen. And if anybody wants to use your fancy computers and go to demo.garlicsoftware.com, you will also see the relative humidity and temperature in my office right this moment. So again, here, I'll take this, copy that. And then as people are hitting it, you'll see that the actual hit sensor, or the hit counter, is going up as you guys are hitting it live right now in my office. So yeah, 20, okay, somebody's going overboard. All right, so anyway, that is the last demo. And that will continue to serve up demo.garlicsoftware.com for a little while. Let's go way in. It's got the name right there. It's just for reference. And temps and humidity. All right. And with that, thank you all. So if you want to get a hold of me, scott@garlicsoftware.com. And if anybody got any question or answers, I'll be around for a bit if you want to hang out and chat. And that's it.
Thank you. Thank you very much, Scott. It was a wonderful presentation, and really end to end, taking us from the classic Blinky all the way up to a web server. So yeah, I think we saw a few questions in the chat. I think the Tariq asked a few, but I believe they left. So if anybody has a question they'd like to ask, I think live people get precedence.
Oh, somebody's gone over 170 queries, really? Somebody's having fun. That's right, my network can handle it.
So I guess I'll take host's prerogative and ask the first question. Did you finish your light model?
I have not. I was actually preparing for this presentation for the past couple of weeks. I gave it also to the Las Vegas Python group, hence where I actually saw the Vegas, the LVO convention there. And that's something I get to work on this coming up week. So I have 4 D&D characters to paint and 1 light pole to hack together. So if anybody is interested, there's wire called magnet wire, which is copper wire that has enamel over it. And there's some super, super thin variants. And actually, that's what I'm going to run in the pole to get the power from the base. So I'm going to 3D print a new base that'll hold my battery and my microcontroller. Then I'll just run the little wires, the magnet wire up the pole into the light fixture.
Awesome. Well, I hope you share a photo or a video of that on the Boston Python Slack when it is complete. Very exciting. Anybody other questions?
I've got a question. Where would you use this, or what would be the benefit of using this over something like the Arduino development environment and language, if you're familiar with that?
Yeah, so Arduino is basically C++, and I love it. And there's lots of functionality that you can do in there. And I have many Arduino boards, probably all of them from all kinds of companies as well. It's a matter of which language do you prefer. So for example, in this microcontroller, the Raspberry Pi 2040 that I'm showing, or the Expressive, which is this particular one, ESP32, That's all in, like, under the hood, it's all in C, right? Like, it's the CircuitPython and MicroPython are implemented in C under this, right? So if you're comfortable in that layer, go for it. Now, the Python implementation on Arduino is lacking. The C implementation on Arduino, perfect, works great. So that's where I draw my lines. Basically, like, if I want to run Python, I'm going to run it on a CircuitPython device or MicroPython device. And if it's going to be an industrial scale, it'll probably be a MicroPython, because CircuitPython is definitely geared towards beginners, and it's excellent for that. I love it. Does that kind of answer your question?
Yes, thank you.
Sure.
I've experimented a little bit with CircuitPython on Adafruit's Circuit Playground, which has a lot of nice little sensors on it, and it's a one nice packaged circuit board. But I haven't tried all the little special purpose boards, many of which you showed tonight. In terms of connecting them together, there's really two options. One is a plug board, what used to be called a breadboard.
Yep.
And the other is 3D printing little scaffolds for them. Do you have recommendations on both plug boards and on a relatively versatile but not too expensive 3D printer that you're using?
Sure. So let me get my camera set up here so I can get up high enough. Get an overhead shot. All right, I'm gonna share just so we can see the camera real quick. All right. So breadboards, super good for prototyping. So you saw two examples on this breadboard here, using the Raspberry Pi Pico and the KB2040. 3D printing, I just 3D printed this little holder on my inexpensive or relatively inexpensive 3D printer. And then you have other boards, and this is another one from Pimeroni. That's a Badger 2040 as well, using an e-ink display, and another ruler, which is just a circuit board. So there's no case, there's no nothing else. It's just a ruler, which is just a circuit board, and it has LED capacitive touch sensing. It's also running CircuitPython, by the way, to do all this. I like being able to have all of these available, right? Like, you're going to get some boards that are going to have just boards, or fancy, there's a keyboard one with, keys, display, dials, all kinds of fun stuff. 3D printing is great if you have the space and the patience for it. You have to tune them. There's lots of, you can see even this 3D print, like there's a big gotcha in the 3D print where it's all goofed up. Like, I don't particularly care because this is just for a demo board. I'm not showing this to just you all and everybody else on YouTube. So it's not that big a deal to me. But at the same time, it's like, I didn't really have the patience to go print that again. Like, it's a waste of my time. It was like, this was good enough, this particular one. I have both kinds of 3D printers, both the melty plastic and the LED kind with the resin. The resins make some beautiful models. I would recommend those if you really like making really detailed 3D prints. The problem is you need a great place to run it and have good exhaust for the resin smells. Those are not good for you or your pets. If you have a pet, like I have a cat sitting right here, and he cannot be around the resin. Breadboards are great, again, for prototype, just trying out stuff. And then you want to have your own circuit boards made if you can. And short of that, if you're just using components and throwing them together like I did for the server example, which is still counting up, somebody's still running that while loop, then yeah, I would just do 3D prints for basic stuff like that and not really care. Like I had, like there was several other examples, and again, these are just they're just orange because that's what I had, right? Like this is a case, and it has the same cutie pie inside of it, and the screen's just screwed onto the back of it. Like it's super nice to have these, but I mean, I could live without that as well. But I've shorted out a couple boards on my desk while having the quarter on my desk. Quarter was not a good plan. It's conductive, but it's great for examples.
I've seen some folks who have they'll get a circuit board made and then do the solder reflow,
Yep.
like an old frying pan with some sand in it in their oven. Have you tried dipping that deep into fabrication?
Yes, and I don't have it right here, right next to me, right this second. But yes, I actually have a full reflow oven. So
Awesome.
I have.
Is it built out of a toaster oven? I know I've seen a lot of.
It's an
or
official.
Do you have a?
It's a full blown
a proper.
Yes. The the nice. You can adjust all of the temperature points and the whole wave for how it heats up and for which kinds of solder. And since I really like leaded solder, I'm not a big fan of the non-lead solder. So I use a lot of toxic solder paste. But yes, if you're interested in that kind of stuff, OSH Park is a great place to get your boards done. It's like $5 a square inch, if I recall, and you get 3 copies of your board. And you can use Eagle CAD if you want to have a very simple app. And there's also open source solutions as well for doing board design. OSH Park there's a partner site that does stencils. So if you want to get into doing reflow or doing surface mount components, there's a stencil site as well. And you can get your stencils and then do your solder paste and do your frying pan if you want, or pick up an inexpensive toaster oven. I don't recommend everybody go out and buy a full reflow oven. It's just takes up space. It's yet more gadgets. But yes, I've done boards. I've done a lot of Bluetooth boards. When Bluetooth beacons first came out, I did a bunch of Bluetooth boards. I've done, actually part of my master's thesis was doing a Bluetooth beacon for Safeway. When you walk into the store, it'll detect you're there and trigger the Safeway app and all that fun stuff.
Cool, thank you.
Sure.
And I think we could maybe squeeze in one more question if somebody has another one for Scott.
Like, how high does the counter go on this display?
I think I saw Patricio raise a hand there.
Yeah, we just want to comment. I saw that you have only a single resistor for the 3 LEDs, but
Yes.
I figure out that they are only a single one is flashing, so it's okay.
Yeah. So yeah, the resistor, I was cheating for this demo example, and
It's
I
okay.
mentioned it. You're limiting the current through that resistor. So your LED is only going to light up so bright based on the resistor. And the problem is when you have 3 LEDs all running at the same time off of one resistor, the current is being divided evenly amongst those 3. So it's going to be slightly dimmer than if you had 3 resistors for, 1 resistor for each LED. So yes, I could have made it pretty and made it brighter, but I was just cheating.
It's cost reducing.
And this is also why I like those NeoPixels, because you don't have to worry about resistors. It's all taken care of inside the NeoPixel. You don't have to do anything. It's all magic.
Cool. Thank you. It was a great presentation. Thank you.
No, thank you.
Yes, thank you again, Scott, for a wonderful presentation. I'm going to cut the recording here. Bye, YouTube.